and then welcome Earle Wilson as our speaker for the SOFLUX webinar this month. Earle is a new assistant professor at Stanford in physical oceanography. He's been involved, he did his PhD at the University of Washington and was a postdoc at Caltech, and he's been involved in the Southern Ocean and the SOCOM effort, and a more expanded work on the Southern Ocean as a postdoc at Caltech. And he's going to talk today, and I don't have your title in front of me, but he's going to talk about his ongoing work on upper ocean processes in the Southern Ocean. So I'll let you go ahead and get started, Earle. Thanks for being here.
Yeah, thank you for the introduction. Let me share my screen.
Looks good.
Okay. All right. Okay, so thank you all for thank you for those who join in and for those who will listen to the recorded version of this talk. So I'm Earle Wilson, and today I'll be talking about drivers of abrupt circumpolar surface warming events across the Southern Ocean. This is work I've been doing on and off for the past few years, starting at University of Washington and then through Caltech. A good portion of this work was done by Natalie Armstrong, who was an undergrad researcher who was working with us when I was at Caltech. And so I want to highlight David Bonin, who's a graduate student at Caltech, working with Andy Thompson, who was my former advisor, and Steve Reiser, who was my PhD advisor at University of Washington. And funding for this project came from NSF and through SOCOM. So I'll start off by showing this movie, which is a time lapse of daily surface temperature anomalies in the Southern Ocean through late 2019 through early 2020. And what you're seeing here is this development of this broad circumpolar scale warming event, which was arguably one of the warmest days in the Southern Ocean of the past 40 years. And so this talk will focus on the drivers that led to this event and what this event and other recent warming events mean for the Southern Ocean going forward. But before we dive into that, I think it's important to establish some context for these recent events. And so here I'm showing a time series of sea surface temperature anomalies over the Southern Ocean, which I've defined here as between 50 south to 65 south. And then the lower plot is Antarctic sea ice extent. And so over the past 10, 15 years, the sort of thing that people have focused on is the fact that the Southern Ocean has really cooled over the circumpolar channel quite robustly. And with that, they've had an expanding sea ice extent all the way through till late 2016. And the patterns are shown here on the right. And you can see that there's near uniform ice growth, sea ice growth, except for in the Bellingshausen Sea and Amundsen Sea region. And corresponding to that is this broad scale cooling that extended well beyond the sea ice zone. And so there have been many mechanisms put forward to explain these surface cooling and sea ice expansion trends. And that includes changes in ice drift, changes in freshwater forcing and ice ocean feedbacks. And the one that I think have caught hold the most is this idea that these trends have been driven by the changes in circumpolar westerlies, in particular the fact that the westerlies have strengthened and shifted poleward. And so here I'm just showing this mechanism. So basically with stronger winds, you end up with increased northward equine transport on relatively fast timescales, which leads to surface cooling. But associated with that is this longer term spin up of the upper cell in the Southern Ocean, which would eventually, we think, lead to upwelling of warm circumpolar deep water in the sea ice region. And so there are two timescales associated with this feedback, and the longer timescale response is this anticipated surface warming and sea ice loss. And so this is the context that we had coming in to late 2016. And then in 2016 onward, the story shifted quite a bit. And so what we've seen is that in the same regions, we've seen quite very prominent warming events in the summer times, in particular late 2016 and late 2019 going into 2020. And these events have been the warmest on record as far as the satellite record is concerned. And associated with that has been like this dramatic meltback retreat of the sea ice extent over this period. And so most studies so far have focused on the loss in sea ice extent, and I've listed a few here. I won't get into too much of these details, but the thing I'm particularly interested in is the warming signal that we've seen in the circumpolar Southern Ocean beyond the sea ice region. And so these plots here show snapshots of surface temperature anomalies for both the 2017 and 2020 events, summer 2016/2017 and summer 2019/2020. And these are like the days where the temperature were warmest. And here, these black contours sort of enclose the areas where the local temperatures were above the 90th percentile. So these were really extreme events. And one could argue they would be classified as marine heat waves for these periods. And so marine heat waves are interesting and very much distinct from the sort of long time scale warming and warming trends I've been talking about earlier. And they are particularly important for ocean processes and biological productivity and so forth. And so in addition to these decadal scale trends that we anticipate due to changes due to circumpolar westerlies and so forth, on top of that, what I think is really important is understanding the drivers of the short time scale extreme events, and one of them being marine heat waves. And so our questions going into this project were as follows. What were the mechanistic drivers of these recent circumpolar warming events, and to what extent were they due to transient variability versus longer term climate change? And then what can we take away from these events and apply to, or how do these events inform our understanding for future events in the Southern Ocean, future SST extremes in the Southern Ocean going forward? And so to investigate these recent warming events, what we did was to construct a circumpolar mixed year heat budget, which I've shown here. And so for our control volume is this region, the circumpolar channel between 50 south and 65 south. And with this control volume, the heat budget is relatively simple. And this is taken from Dong et al. 2007, who did a seasonal heat budget for the Southern Ocean quite a few years ago. And so the mixer tendency, this integrated mixer tendency is due to ERC heating, northward advection, and vertical entrainment to a good approximation on seasonal timescales. And here I'm just showing schematically what that looks like. This section plot across our control volume. And so we constructed this budget using observations and reanalyses. For the ERC heat fluxes, we use the ERA5 reanalysis. For the upper ocean temperature salinity, we use the Gilson Argo data set. And then we define the mixture depth using a density threshold where of 0.03 kilogram per meter cube. And because this vertical entrainment term is very sensitive to sub-monthly variability, there's no easy way to get at that from observations, at least on the circumpolar scale. So we infer that as a residual, which we'll sort of look at in more detail later on. And so this is what the mixer heat budget looks like over the Argo period. And so the black line here shows the mixture temperature tendency, which makes sense. It's positive in the summer from spring through summer, and negative from fall through winter. And the dominant terms here is the ERC heat flux, which you can see here in green. And this Ekman term is just generally cool because the westerlies are always there. And the residual here is shown by the dash gray line, which we interpret as mostly due to entrainment. It could be due to other smaller terms, but we think it's mostly due to entrainment. And so in the summertime, this term is negative, so it's acting to cool the mixed layer because you have this warm mixed layer above, relatively cool water below. So any mixing will introduce cooling to the mixed layer. And in the winter time, it's positive because at that point, the mixed layer is past the seasonal picnic line is gone, and the mixed layer is in direct contact with circumpolar deep water, especially near the ice edge. And so you end up entraining warm water in the winter time. So we think the entrainment, that this residual is indicative of entrainment for the most part. And so this plot at the bottom shows the same thing, but with the seasonal, with the monthly means removed. So these are showing the monthly anomalies. And here I've highlighted the two warming periods of interest. And so in both cases, what was really prominent was the fact that this ERC heating term was really large. And that was the #1 contributor to the warming event. And associated with that was also an increase in the Ekman warming due to Ekman transport. But by far, the dominant term was this amplified ERC heat-in, which in this particular case was slightly offset by, or strongly offset by enhanced cooling due to entrainment. And so digging into these, the ERC heat flux terms a little bit more. So they were really large, but they weren't large due to the fact that the ERC heat fluxes were large. And so this top plot is showing the net surface heat fluxes, the anomalies over the year 5 period. And if you look at the black line here for the two warming events, the black line, you see that they don't reflect this term was not anomalously large. And so during the 2016-2017 event, it was actually negative. So the ERC heat fluxes were weaker than normal, so there was less ocean warming. And the same thing here for the second event in 2019-2020. And if you look at the patterns, so in here, I'm showing the October through December for 2016, the mixer temperature tendencies are on the left, and on the right, we have the ERC heat fluxes. You do see some correspondence, but the patterns don't quite line up. And in 2019 through 2020, or in 2019, it's even more different. And so, this amplified ERC heat-in wasn't due to the ERC heat fluxes themselves. And as I'll show, it was actually due to the fact that the mixer depth was shallower. And so what was really different during these periods was the fact that the wind stress was really weak. So the circumpolar westerlies, they died down by a factor of 25% towards 50% in some regions. And here you can see that how that stands out in the record. And so right in the lead up to these warming events, you can see the strong weakening of the circumpolar westerlies. And again, here I'm showing the mixer temperature tendencies on the left. And here in the middle, I'm showing the wind stress anomalies, which were pretty circumpolar in both cases. And associated with that were this shoaling anomaly in the mixed layer depth. And so from this, we inferred that the weaker winds led to a shoaling of the mixed layer due to the fact that in this time of the year, what sets the mixed layer depth is wind-driven entrainment, and due to the winds being weaker, we end up with the mixed layer shoaling. And this is consistent with recent work done by Panassa et al. In 2018. And so to summarize that, here again, I'm showing the mixer heat budget. And so rather than show the time series, what I'm showing is just this budget in the phase space defined by net ERC heat fluxes on the y-axis and mixer depth on the x-axis. And colored in the background is the sum of the heat tendencies due to air-sea heat fluxes and the Ekman transport. And so, and here these lines show just trajectories in this phase space over the Argot period. And so the black line shows the climatology, and the gray line shows just the trajectories for each individual year. And so in the top left quadrant is the situation in the summertime where the mixed air depth is shallow and the air-sea fluxes are high. And so you end up with this really high combined warming due to air-sea heat fluxes and the Ekman term. And then on the opposite end, we have the situation for winter where you have very deep mixed layers and strong cooling. And so what stands out here is for the two warming events in 2016 and 2019, shown by the green lines, is the fact that the mixed layer depth was really shallow, or showed very strongly in November in the fall from October through November. And so what that did was to set the heat budget on this different trajectory that has faster warming, and that led to the record-breaking temperatures we saw in the summertime. And so we've established that these warming events were due to the wind stress anomalies being anomaly weak. And so we wanted to dig into that a little bit more. And so again, here we have the time series of wind stress anomalies on the bottom and the heat flux anomalies on top. And it wasn't super obvious to us, like why, yes, the winds were really weak, but you look in the record, you can find similar events, if not stronger events, more negative wind stress anomaly events. And so we wanted to dig into that a little bit more. And so what we did was to just construct this 1D mixed air mixing model that's loosely based on the cross-center mixed layer model. And so this is a 3-layer model. We have a mixed layer on the surface, there's this transition layer below, this picnic line, and then we have the deep ocean, which is held constant. And this model is forced by wind stress at the surface and also air-sea heat fluxes and freshwater fluxes. But actually, for what I'm showing here, it was only just the heat fluxes. I won't get into the detail, but essentially what this model does is that you force it with the air-sea heat fluxes, and you can compute that you can convert that into like a potential energy change, and then you can compare that to the potential energy change due to wind mixing, and you can solve essentially for the mixed layer depth in that way. So you're getting the mixing layer depth as opposed to the mixed layer depth. And happy to go into that in more details, but moving on. And so what we did was to force this model with sort of idealized air-sea heat fluxes from October 1 through March, so from spring through the end of summer. And what we did were these ensemble studies. So we did 6 ensemble experiments where we forced the model with these synthetic winds, which sort of mimic what we see in the Southern Ocean. And each ensemble had 200 members. And what we did, we had this control, which is the wind stress being roughly 0.1 Newton per meter squared. And then at different points in the time series, we weakened them by 50%. And so, which you can see here. And so when we weaken the winds, we're changing the mean value of the winds, and while keeping the variability constant, which is actually important. So you still have effectively storms and so forth, but it's just the timing that's different. And so we apply the perturbations at different time, and we wanted to see the sensitivity of the mixed layer response to the timing of these wind perturbations. And so the results are shown here. So on the left, we have the forcing. On the right plot, we have the mixed layer depth response, mixed layer temperature response in the middle, and below we have the mixed layer temperature tendency, the rate of change of mixed layer temperature. And so as you would expect, when you weaken the winds, mixed layer depth shoals, and the timing lines up pretty well. with when we apply the force in. And what I'm showing here on the right is just the control run subtracted off to show the anomalies more clearly. And the big takeaway is that when you apply the wind stress force in December, January, you have the strongest response, and it's like almost an order of magnitude different from similar wind stress force in applied in October versus December. And so it's very sensitive to the time in, and that's due to the combination of the surface heat fluxes being near maximum at around that time, but also the fact that the mixture depth is also extremely shallow. And so if you're on either side of the shoulder of the mixture depth increasing, then you won't get as strong of a response. And so that's essentially what happened in those two events. That the winds died at exactly the right time for you to get this maximal response in surface temperature. And so the other thing that comes from that is that there's also this very strong compensation due to entrainment. And so if you imagine this case on the left, where you have sort of the normal case, mixed layer being forced by winds, and you have surface heat in. And if you were to weaken the winds, what happens, we think, is that you end up shouldering the mixed layer. And so now you're applying the heat over a thinner mixed layer. And so now you have this stronger temperature gradient and a thinner mixed layer. And so even though the winds are weaker, the fact that the mixed layer is shallower leads to, you still end up getting this relatively strong entrainment, which helps to dampen the effect of the warming due to the air sea heat fluxes. And so the big takeaway is that the timing is important, and also which I didn't really emphasize is the fact that the variability of the winds are also important, because you still need these high frequency events to come through and drive the mix in during these quiet periods and help dampen the strong cooling. And so to kind of step back, the other thing that we were interested in is to what extent were these anomalies due to just internal variability or longer term climate change, right? And so far we've looked at how weaker westerlies or weaker surface winds could lead to reduced open transport and mixed air shoaling, which together can combine to give extreme summertime SSTs. Stepping further back, what we've found is that these events were associated with strong negative southern annular mode events, in particular in austral spring. And so this is not particularly new. The fact that negative sound is known to weaken westerlies and lead to warming. And here I'm just showing the surface pressure anomalies associated with positive sound. And so, like I said, quite a few studies have looked at, it's well established that, that negative SAM events can lead to warming in the Southern Ocean. And also, and ENSO as well can lead to strong temperature changes along the circumpolar channel. And so here I'm showing the surface temperature response to positive SAM, which is a cooling, which leads to cooling in the circumpolar channel and warming at mid latitudes, and positive ENSO events, which have a very similar latitude profile, but more concentrated in the Pacific region. And so, could these events simply explain what we saw in 2016 and 2019? So to answer this question, we looked at the output from the CSM1 large ensemble. And so this is a climate model that was run many times with slightly different initial conditions, and the spread in the resulting simulations give you a sense of internal variability. And so this is a good way to assess whether changes we see are due to natural variability or just internal variability. And so this is sort of the main takeaway from that analysis. And so these plots here, the blue bars are showing the probability density from the CSM1 large ensemble. This is for spring SAM events in the ensemble. and these red lines here show the SAM anomalies we saw in recent years. And so what we see is that these SAM events, these negative SAM events that we saw in observations are indeed rare, but not outside the realm of possibilities for as predicted by the CSM1 large ensemble. And this is for the same 40-year period that we have for the observations. And on the right, I'm showing a similar thing, but just a subdimension SSD. And again, like we're comparing the spread we see in the ensemble to the observations. We see that the observations will be rare in this world that defined by CSM1, but not completely unexpected. And so these plots here show composites of the SSC Warman response on the left due to ENSO on the y-axis and SAM on the x-axis, and colored is the SST anomaly. And so with negative SAM events, we see strong warming in CSM1, and the circles here show the observations. And so what we see are two things. One, for these months, the SST anomalies are almost entirely driven by SAM variability, very weak dependence on ENSO in the ensemble average. And the SST response we see agrees well. The SST response simulated by the CSM1 ensemble agrees well with observations. And so those are the two big takeaways. And on the right, it's the same thing, but just showing mixed layer depth anomalies. And again, we see the strong dependence on SAM over ENSO for this time of year. And the response that we see are the response between observations and the model simulation are very good. And so the big takeaway is that this is essentially just an extreme manifestation of internal variability from what we can tell, and you don't need to invoke any other mechanism, any other longer time scale mechanism to explain these changes. So the summary here, to recap, is these recent circumpolar warming events were initiated by rare late year negative SAM events, which led to weaker circumpolar westerlies, reduced northward Ekman transport, and an accelerated shoaling of the mixed layer. And these shallow mixed layers led to an amplified warming during the late spring, when you have the surface air heat fluxes are at their seasonal maximum. And like though these events are rare, they're not outside the envelope of internal variability, at least as defined by these CSM1 simulations. And so these results are in this manuscript that we've written and submitted, and it's currently in review. But if you want to check it out, we have it on. You can access it in this open access archive. And so some closing thoughts. So what I've talked about so far is just recent changes, but now looking ahead, what could we expect? So one takeaway from our results is the fact that the mixed layer depth is super critical for establishing the range of possibilities for how extreme SSTs can be in the summertime. And the mixed layer depth is changing in interesting ways. And so currently what studies have found is that the Southern Ocean mixed layer depth is actually deepening. And at the same time, the stratification beneath the mixed layer depth is strengthening. And so that's due to two things. That's due to the winds being stronger, and the Southern Ocean just generally being more stormy, which drives deeper mixed layer depths. But at the same time, you have increased surface warming, increased surface freshening. So combined, that gives you a stronger pit decline. And so the question in my mind is, how do these competing processes, how will they fare going forward, and which one's going to win out? And if these trends continue, how will that play? How will that impact the Ocean SST extremes? And then the second thing that I think is interesting is the trends in the southern annular mode itself. So so far, there's been this pretty robust trend towards positive SAM conditions, so stronger westerlies, more stormy Southern Ocean. And over the past few decades, that has been mainly driven by the loss of ozone, stratospheric ozone over Antarctica. But in recent years, studies have shown that the ozone is recovering, this was shown by Banerjee et al. In 2020. And so the ozone is recovering, but at the same time, you also have increased greenhouse gases, which also has a tendency to push the SAM towards a more positive state. And so what we anticipate is in the future is that at some point the ozone forcing will go away, and at some point the greenhouse gas forcing may actually take over and help to sustain this trend towards positive SAM. But there's a key difference between the two types of forcing. With ozone forcing, the trends in SAM are mostly in the summertime, but with the greenhouse gas forcing, we don't expect that strong seasonal bias. And so, so how that plays out, I think, will be really important, not just for mean states of the ocean SSDs, but also the extremes that that can occur, and the seasonality of these changes will be critical. And so with that, I'll end a little bit early and take any questions if there are any.
Well, thanks for a great talk. Big round of applause. And questions? Maybe I'll start by asking, you presented this really compelling explanation for the marine heat wave events. Does freshwater or ice melt have any role in, or do you need to invoke it in any way to explain the events in the last few years?
Yeah, that's a good question. We haven't looked explicitly at the freshwater forcing, so we looked at precipitation, and so what we saw is that, you know, during these particular events, precipitation wasn't much different from normal, just like the ERC heat fluxes weren't much different from normal. But stepping back, we have seen, you know, there are these freshwater trends, and so we think that may have an impact of just the background mean state of the Southern Ocean, and so like kind of like what I was saying towards the end, if those trends can continue, especially if the winds sort of die down due to the ozone recovering, then I think that could be an important process to impact the ERC heat fluxes on the SST extremes going forward.
Great. Yeah, I see that Simon Josie has his hand up.
Yeah, can you hear me?
Yeah.
Yeah, I can hear you.
I really enjoyed that, what I could hear of it. Unfortunately, my internet was dropping out, so I missed big chunks of it, I'm afraid, but I definitely listened to the recording as well. But yeah, really nice. And obviously, you used ERA 5. I mean, this is an obvious question. You used ERA 5, and we know how notoriously divergent the flux data sets are in the Southern Ocean. So I wondered if you, and that's in terms of the long-term means, I guess, they may be better in terms of variability. Did you look at another data set to like NCEP or something like that to see if you got similar results?
Yeah. So that's a good question, and so we did look at least we looked at wind variability NCEP, and we did see the wind events in the NCEP reanalysis. If you compare everything, like you can definitely see differences between NCEP and ERA 5, but the story doesn't change. And yeah, which one's right is unclear. You know, they're both
I was thinking,
elaborate interpolations of very sparse data. So
exactly, yeah. Because I was thinking there was a slide early on where you had the heat flux contribution. I think that was what it was, and compared it with the heat content change or something like that. And the patterns, you noted that there was some, it was very interesting because the patterns were similar in some parts and not in others.
Mhm.
I don't think it was just random. And I just wondered if you
Right.
got the same pattern out for that particular event. From
Right.
end-
Yeah.
what it looked like.
That's a good question. I don't think we really interrogated the patterns that we didn't like analyze the patterns that closely between the different reanalysis products, and that's something we can certainly do, and not just with NSEP, but there are other products out there.
Yeah, you know, Sarah's looked good at JRA, for example. You could look at JRA.
Right, right. That's a really good suggestion. Yeah.
Anyway, yeah, I don't want to hold the question,
Yeah,
so
thanks.
thank you very much. Really nice.
Other questions? Yeah, Marcel has his hand up.
Yeah, I agree. Very nice talk, Earle. Thanks so much.
Mhm.
So obviously, I mean, your results are extremely compelling, and I think, you know, I have no reason to disagree with them. But the one question I have is, you know, a lot of the processes you're thinking about are one-dimensional processes that are controlling mixed layer depth variability, winds and shutting down of the winds.
Mhm.
So where I'm going with this is what do you think the role of sort of sub-mesoscale or smaller scale lateral processes have in changing the mixed layer depth? And I really liked how you sort of at the end looked forward to think about how the mixed layer is changing in the coming decades. And have you thought a little bit about how any role sub-mesoscales may have in changing mixed layer depth variability and the impacts on your results?
Right. Yeah, that's an excellent question, and so the short answer is that I think sub-mesoscale processes are incredibly important if you're looking at like local changes, and so this analysis we sort of, you know, we looked at the 0th order effect, this is circumpolar averages, and I showed the patterns but didn't really explain the patterns, and so if you want to explain, you know, patterns in one basin or in one part of the basin, and then smaller scales, you absolutely need to invoke, you know, lateral, you know, advective processes and so forth. But then I also think, yeah, towards your larger point, I do think there's potential that even in the larger scale, that sub-mesoscale processes could have an imprint on the circumpolar averages itself. But that's not something I've looked at in detail. Yeah, and
it's a tricky thing to do.
it's a tricky thing to do, and I'm not sure how. I guess I'm not quite sure how one would go about it, but I think that's very important.
Yeah, I guess thinking about, you know, the increase in available potential energy by deepening mixed layers going forward, and what that might encourage sub-mesoscale processes to sort of increase or become more active. I think it's an interesting question, but yeah, it's tricky with the data sets we have.
Yeah, absolutely, and there have been quite a few studies that came out recently. I can't remember the authors. I think you may be affiliated with some of them that looked at, you know, local mixed area heat budgets using like glider data, and that was like one of the key results that came out of those studies. And so yeah, I agree. Like I think I think smaller scale local studies is like kind of the way to go for now, and we'd be interested to kind of see some more modeling work in that area.
Yeah, thanks.
Other questions? I wanted to ask about the change in northward Ekman transport, because I was thinking that must be more subtle than just saying the Ekman transport has changed, since it must depend on where the zero wind stress curl is and whether the northward Ekman transport is carrying cold water or warm water. Is that something you looked at? Is that something that is there another layer to that that I just missed in what you presented?
Right. So So
I guess I'm thinking if you have the Ekman transport is responding to upwelled water and you're upwelling cold water, that would look different than if it's a question of how it's transporting surface water.
Right. So yeah, so I guess my argument is like actually very simple, right? And so because the time scales involved, we're just looking at the near surface, just immediate response. So if you weaken the winds, you're reducing the extent to which the winds that when transporting water, like cold water, across the channel. And so I guess what you're getting at is like the longer time scale, like the upper ocean spin up of the upper cell. But that in my mind is like a longer time scale than the events that we're looking at, which kind of manifest over weeks, 1 month. And so, right, yeah. So I think for this, it is quite simple. And if you're thinking about certainly the upper ocean adjustment to sustained trends in the circumpolar westerlies, then you need to think about the three-dimensional overturning circulation more carefully.
Yeah, it's nice that you managed to avoid getting in the weeds on that. Marcel, you have your hand up.
So I'm just now thinking. See, the results you show with the time changes in the wind and the reduction in the strength of the wind, it's averaged over some time, right? Like a monthly average or annual averages. Do you have any indication of if that's due to a drop in the strength of storms themselves, or is it a reduction in the frequency of storms that is creating this time mean reduction in the wind?
That's an excellent question. Yeah. So that's actually on my list of things to do as I work on the revisions for this paper. Yeah, we've only looked at the monthly mean variability, and to get at the storm question, you sort of need to go from monthly down to like sub-daily timescales, and that's it's definitely doable. Just to work with a lot more data. But to what extent was it just like a annual mean response versus a reduction in the extremes in the storm extremes? It's not clear to me right now. I've looked at like individual just areas, and you still do see like storm events come through. So it's not like the storm's completely died, at least from what I've seen. But I don't know what the circumpolar picture looks like.
I see. Yeah.
So it may just be less frequent storms. Yeah.
Yeah, it makes sense. Cool. Thanks.
I see that Simon has his hand up. Yeah.
I wouldn't mind asking another one if I can. And it was the bit which, unfortunately, I missed something of what you were saying because of the internet problems. But you were looking then in the second half of the talk at, I think it was a community Earth system model, and looking at distributions of temperature anomalies with the value for the ENSO or whatever it was, Southern Oscillation Index. But I wasn't sure, those temperature values, were they like a circumpolar average?
Right.
And if so, you kind of think about marine heat waves and whatever, they're quite localized, as you could see in some of your plots. So I wonder if your conclusion that it's due to internal variability or consistent with internal variability is because you're not looking on a small enough scale, maybe.
Right. That's an interesting point. Yeah. So the temperature anomalies we were looking at in the CSM1, we were looking at circumpolar averages, and I'm trying to think how a situation where the individual like localized regions could be driven by a different process than the circumpolar average, and it's I guess I can't rule it out, but like I'm trying to think of like how that could happen. So my response is that possibly, yeah.
I mean, so one thing I'm aware of, partly because I've been working on it recently, is the sort of asymmetry side of the Southern Ocean heat forcing and the wind forcing as well. And the asymmetry moves south in the Pacific sector. So it could be that the wind response is different in different regions, or that balance of the heat flux. I mean, it wouldn't be too hard to get some localized differences, I wouldn't have thought. But
yeah,
it's more tricky.
Yeah, that is I know that's what you're saying. Yeah, I think that's definitely a possibility. We haven't looked into it. It could be that there is some asymmetrical anthropogenic signal in either the mixture depths or the wind shifts, and that could have like amplified a region, you know, beyond like, you know, the annual the circumpolar average. But yeah, so that's something we could look into more closely. But yeah, I know I see what you're saying. Yeah,
you can't do everything up front.
Yeah.
It was published as well. I think something flashed past, and it said, and part of the work was published in Earth Systems Science Discussions or whatever it was.
Well, it's in review in Journal of Climate, and well, we're revising the manuscript, but the preprint is available here.
Okay. Yeah. Fabulous. Yeah. Thank you.
Any other questions? Well, if not, we'll wrap up here. Thank you very much for a really wonderful talk and another round of virtual applause.
Thank you.
Really great presentation and really stimulating discussion.
Yeah, thank you for all the questions and for hosting me.
Yeah, thanks very much, Earle. That was really great.
Let's stop recording.